A rocky planet circles a dim red star just 48 light-years from Earth. For years, worlds like this were only dots in telescope data, places we could measure but never truly imagine. Now astronomers say one of them may hold the first detected atmosphere ever found around an Earth-sized planet inside a star's habitable zone. That claim is extraordinary, because air changes everything. An atmosphere can move heat from day to night, shield a surface from radiation, sculpt clouds, power weather, and preserve the chemistry that life would need to gain a foothold. If the result stands up, this is not proof of alien life, but it is a huge step toward finding a planet that feels less like bare rock and more like a real world. The planet at the center of this story is called L98-59F. It orbits a small red dwarf star in the southern sky, and it belongs to a compact family of worlds that has fascinated astronomers for years. Several of its sibling planets race around their star in tight, hot orbits, but this outer world appears to sit in the star's temperate zone, where liquid water could exist if conditions are right. Red dwarfs matter because they are the most common stars in our galaxy. They are smaller, cooler, and dimmer than the Sun, so their habitable zones sit much closer in. That makes their planets easier to detect, but it also creates a problem, because the same stars can be stormy and violent, blasting nearby worlds with flares and ultraviolet radiation that may strip atmospheres away. That is why the new report matters so much. Finding a temperate rocky planet is exciting, but finding one that may have held on to an atmosphere despite living near an active red dwarf is the real scientific prize. It means nature may be better at building resilient worlds than we once thought. So how do astronomers detect air around a planet that they cannot directly see? They wait for the planet to pass in front of its star, a transit that causes the starlight to dip by a tiny amount. During that crossing, a small fraction of the light filters through the planet's upper atmosphere, and molecules there can absorb specific colors, leaving behind faint spectral fingerprints. Those fingerprints are unbelievably subtle. Researchers are not looking at oceans, mountains, or blue skies. They are measuring vanishingly small changes in starlight with instruments so sensitive that the entire experiment depends on precision, patience, and repeated observations lined up with orbital timing that has to be known almost perfectly. That is where the James Webb Space Telescope enters the picture. Webb was built to look deep into the infrared, a region of light where many atmospheric gases reveal themselves more clearly. Its giant mirror and exquisitely stable instruments allow astronomers to analyze exoplanet transits with a level of detail that simply was not possible a decade ago. In the case of L98-59F, Webb appears to have detected evidence consistent with an atmosphere rather than a bare, airless rock. Scientists are still testing which gases best fit the data, and they are careful not to oversell the result. But even the possibility is enough to electrify the exoplanet community, because a habitable zone rocky planet with air has been one of the field's biggest missing pieces. Imagine two versions of the same planet. In one version, the star's radiation stripped the air away long ago, leaving naked stone baked on the daylight side and frozen in darkness on the night side. In the other version, a blanket of gas smooths out those temperature extremes, allowing cloud layers, climate cycles, and perhaps even stable reservoirs of liquid water. The difference between those two worlds would be dramatic, and yet from Earth they might look nearly identical until you inspect the spectrum. That is why atmosphere detection is such a turning point. It lets astronomers move beyond simple census-taking and start describing what these planets are actually like. There is another reason researchers are excited about this system. The L98-59 family contains multiple rocky planets of different sizes and temperatures, all orbiting the same star. That gives scientists a natural laboratory, a chance to compare sister worlds that formed from the same disk of material but evolved under different levels of heat and radiation. Think of it as a cosmic experiment in planetary survival. The inner planets may have lost volatiles, seen their surfaces melted or sterilized, or turned into dry mineral worlds. Farther out, L98-59F may represent a threshold case, distant enough to remain temperate, yet close enough that its star still tests the durability of any atmosphere it carries. Of course, detecting an atmosphere is not the same thing as proving habitability. Venus has a thick atmosphere, but it is a hellish pressure cooker. Titan has a dense atmosphere too, yet its seas are made of liquid hydrocarbons under brutal cold. Air alone is not enough, its composition, pressure, chemistry, and long-term stability all matter. Scientists will want to know whether this atmosphere is rich in carbon dioxide, water vapor, nitrogen, or something stranger. They will ask whether the planet is wrapped in haze, whether clouds are muting the spectral signal, and whether the heat is distributed in a way that suggests winds and circulation. Every new piece of data will help determine whether this is a mild world, a hostile one, or something in between. There is also the challenge of false positives. Stellar activity can mimic or distort atmospheric signals, especially around red dwarfs whose surfaces can be modeled with spots and magnetic chaos. Instrument systematics, data reduction choices, and modeling assumptions can all nudge the answer one way or another, which is why independent teams will scrutinize the claim from every angle. That scrutiny is not a weakness, it is the scientific process doing its job. The most important exoplanet discoveries are rarely settled in one dramatic moment. They harden gradually, through reanalysis, follow-up observations, competing models, and the slow convergence of evidence until a once radical idea becomes the new baseline reality. If L98 to 59F keeps passing those tests, the implications are enormous. It would suggest that rocky planets in habitable zones around red dwarfs can preserve atmospheres after all, at least in some cases. Because red dwarfs dominate the Milky Way, that would instantly expand the number of potentially life-friendly worlds that astronomers can target in future surveys. And that future is already taking shape. Webb can continue to probe atmospheres, but it is also paving the way for the Nancy Grace Roman Space Telescope, the extremely large telescope, and a new generation of observatories designed to directly characterize Earth-sized exoplanets. Each instrument adds a piece of the puzzle, from better transit data to improved atmospheric models and, eventually, the dream of detecting true biosignatures. Biosignatures are patterns in atmospheric chemistry that may be difficult to explain without life. On Earth, oxygen and methane together are a powerful example because they react away unless something keeps replenishing them. But scientists are careful here too, because planets can surprise us, and geology, photochemistry, or exotic climates can sometimes imitate the fingerprints we most want to trust. That is why the discovery of an atmosphere is so important even before life enters the conversation. You cannot search seriously for biosignatures on a planet that has no detectable air to study. First you need a target with enough atmosphere for chemistry to happen in a measurable way, and only then can the deeper hunt begin. There is a philosophical side to this story as well. For most of human history, planets beyond the solar system were pure speculation, imagined in poetry long before they were found by instruments. Now we are crossing into an era where we can discuss the climate of a rocky world around another star with real data rather than fantasy. That shift changes our place in the cosmos. Earth stops feeling like the only detailed example and becomes the first case in a growing catalog of worlds with weather, chemistry, and perhaps one day biology. Every atmosphere we detect makes the universe seem less empty and more populated with environments, each carrying its own story of formation, loss, and survival. L98 to 59F may not be a second Earth. It may turn out to be cloudy, dry, carbon-heavy, or harsher than the headlines suggest. But even that would matter, because science advances not by finding comforting copies of home, but by mapping the full diversity of nature and learning where the boundaries of habitability really lie. For now, the most honest conclusion is also the most exciting one. Astronomers may have found the first atmosphere around an Earth-sized planet in the habitable zone of another star, and if that result holds, we are witnessing a milestone in the search for living worlds. The signal is faint, the questions are many, and the follow-up will be intense, but the doorway has opened. One of the most fascinating possibilities is that planets like this could teach us about Earth's own deep past. Before our world became oxygen-rich, its atmosphere was shaped by volcanism, impacts, sunlight, oceans, and microbial life acting over immense spans of time. A rocky exoplanet in the habitable zone gives scientists a chance to compare that long planetary story against an entirely different starting point around a different kind of star. That comparison may reveal that habitability is not a single condition but a long negotiation. A world can begin promising and then fail, or begin hostile and slowly stabilize as its interior, surface, and atmosphere interact. Plate tectonics, magnetic fields, volatile delivery from comets, and the chemistry of rocks all might decide whether a planet becomes barren, temperate, or briefly habitable before sliding into another state. This is also why astronomers care about timing. Red dwarfs can spend their youth in especially active phases, pouring out energy that could erode atmospheres early on. If L98-59F still has air today, then perhaps it formed with a large volatile inventory, or perhaps geological outgassing rebuilt part of its atmosphere after the worst stellar violence had passed. That raises a beautiful possibility: some planets may be survivors rather than lucky exceptions. They may endure intense beginnings and still emerge with enough atmosphere to sustain a climate. If that turns out to be common, the galaxy could be filled with more living candidates than pessimistic models once allowed. Somewhere out there, a small rocky planet may be carrying winds beneath an alien sky. 48 light-years is unimaginably far for humans, yet for astronomy it is close enough to study, test, and return to again and again. In that narrow beam of filtered starlight, we may be seeing the beginning of a new chapter, the moment exoplanets stopped being points of light and started becoming places.